Hello boys and girls, welcome to another episode of FoulkesBrau. Today is Monday, April the 27th. It's day 32 of lockdown in South Africa. Of course, on Friday we're supposed to be going to level 4 of the lockdown. It doesn't really mean much. They're supposed to be relaxing a few things. In other words, now you can buy baby clothes and I don't know what. You still can't buy alcohol. Apparently you can buy cigarettes legally. But anyway, our figures as of last night, 4546 on the infections. It's grown. We're still above 100 a day. In fact, the infections per day are now 185. The average infections per day since the beginning of this, 114.39. Number of deaths we've had so far, 87. Day-on-day growth, 4.24. We've conducted 168,643 tests so far. Tests per day, we're getting there, 7,659. Percentage of infections, 2.7. Percentage of the population tested, 0.28. Our mortality rate, 1.91. Our confidence interval, 95% confidence interval stay is growing, 26.22, obviously because we're getting more infections. But our confidence interval plus our mean is now sitting at 140.61. Our average infection or mean over the last 7 days, 198. So we are 58 above that. So yeah, it is what it is. Anyway, today I thought we would come back to this power monitor circuit that we have been that we started the design with. And just to recap, I've actually made things neater. We'll have our live neutral and earth coming in, so we'll have a chassis mains earth. We have a double pole switch to isolate it. We have a fuse to break it. We have these metal oxide varistors, and you can see I've gone and put in the part numbers and done some selection in the background. I've also neatened the drawing up. BC 7772 or B77720. I chose them because now there is a bit of maths behind this, but there's also some rules of thumbs. Remember, in South Africa we are dealing with 230 to 240 mains nominal at 50 hertz. So the B77720, it's a 630 picofarad 100 amp MOV, clamping 710 volt, AC max 275 volts. We don't know the transformer VA that we need yet, and we don't know the diode bridge yet. You can see we've used a LM317, an adjustable voltage regulator, and I've gone and filled in these capacitor values as well as that one, and these resistor values. That one we don't know yet because we don't know what current we are going to pull. These capacitor values and the resistor values are actually very easy. All we have to do to get that is to go and look at the data sheet. So let's bring that up. We'll bring our KiCad one down. So if we look at the LM317, its output voltage range adjustable from 1.25 to 37 volts. Output current greater than 1.5 amp, internal short circuit, current limiting, thermal overload protection, output safe area compensation, and it's got a whole lot of applications that we can go through if you really wanted to. What we want to know is the device is an adjustable 3-terminal positive voltage regulator capable of supplying more than 1.5 amp over an output range of 1.25 to 37 volts. It requires only 2 external resistors to set the output voltage. It features a typical line regulation of 0.01% and a typical load regulation of 0.1%, so you shouldn't have much ripple on it. It includes current limiting, thermal overload protection, and safe operating area protection. Overload protection remains functional even if the adjust terminal is disconnected. And then they give you a typical battery charger circuit application for it. But what we want to do is come down to, we don't care about any of that, so they give us some nice graphs and stuff, transient load response, load transient response, blah blah blah. And we'll come down a bit and we'll come to the detailed description. And they give you a bit of a description, they give you the functional block diagram. And what we can see is we have a 1.25 volt reference. It's got an NPN Darlington pair output drive, op-amp comparator in there, over temperature and over current protection, your input adjust and your out. Programmable feedback. You can provide easy output voltage or current, not both. So you can either do current regulation or voltage regulation. We don't care about any of that. What we do care about, operation and self-protection, application and implementation. So the flexibility of the 317 allows it to be configured to take on many different functions in DC power applications. And they give you an adjustable voltage regulator, typical circuit. And what we can see is there's a capacitor. There's on our adjust, there's the adjustable resistor, fixed resistor to give us a reference. Another capacitor for the adjust, and another capacitor for the output ripple and the input bypass. And they're using a clamping diode, a 1N4002 R1 and R2. The design requirements are required to set the output voltage. C adjust is recommended to improve ripple rejection, which we've just said. It prevents amplification of the ripple. CI, the input, is recommended, particularly if the regulator is not in close proximity to the power supply. Filter capacitors, 0.1 or 1 microfarad ceramic or tantalum capacitor provides sufficient bypassing for most applications. C out, CO over there, improves transient response. Protection diode D2 is used if C adjust is used. The diode provides a low impedance discharge path to prevent the capacitor from discharging into the output of the regulator. So it's our clamping diode. Protection diode D1 is recommended if C out is used. The diode provides a low impedance discharge path to prevent the capacitor from discharging into the output. So instead of the capacitor discharging into there, it can go back there. Right, V out is calculated in equation 1. So V out, the reference is 1 plus R2 over R1 plus I adjust over R2 for that application. And so they go on, and we have lots of different circuits that we can look at. We have a adjustable regulator with improved ripple rejection, which is basically what we've put in. So we've got our 0.1. Forget the values here. We have different values, and that is calculated to give us our 18 volts out here, and there's multiple calculators for that. But anyway, you will see we've got a 0.1, a 10, and a 1. So if we come back to our KiCad, we've got 0.1 or 100 nanofarad, 0.1 100 nanofarad or 0.1 microfarad, 10 microfarad, 1 microfarad. So to keep our units the same, instead of 100 nanofarad, I'm going to put here 0.1 UF. So we will keep our SI units the same. As I've said, the resistor divider network here is calculated by the formula given in the data sheet. I'm not using a 1N4002, I'm going to use a 1N5819, and of course we could put that flyback diode across there, and let's rotate it like that. And we'll just put it in nice and neatly here. We can draw it in like that, or whatever. So we've put in another protection diode for that capacitor there. So there we have the discharge capacitor or clamping diode for that capacitor, that diode there, and the clamping or discharge diode for that capacitor is over there. So again, we've taken the recommended capacitance values as given to us by the data sheet, and these values we calculated by the formula given in the data sheet, which if we come further down to the data sheet will give it tracking regulator, that is current, battery charger, blah blah blah, more. Okay, they give us some layout guidelines if you're doing your own PC board layouts. Now this specific one, I don't see it, but they don't seem to be giving us the formula to program it. Okay. Okay, there we go. V out is calculated in equation 1. Where does it take it? Is the voltage reference, in other words 1.25, multiplied 1 plus R2 divided by R1 plus I adjust times R2. So what they're saying, the output voltage here is the voltage reference 1.25 multiplied 1 plus R2 divided by R1 plus I adjust the 50 microamp times R2. So we've got 50 microamp going into here. And if we plug all this together, we will get these resistor values here of 240 and 820. I've chosen 15819s because they're Schottky diodes, and if we go and look at the data sheet for that, let's come down. They are low drop power Schottky rectifier diodes, very small conduction losses, negligible switching losses, extremely fast switching, low forward voltage drop, avalanche capability specified. They're suitable for switch mode power supplies, power high frequency DC to DC converters, etc., etc., etc. The thing is, these are fairly common jelly bean components, so you should have plenty of them in your box, and they're pretty cheap. The other diodes that I have plenty of are these 1N4 series, typically the 1N4007. They are probably the same price, they're just not Schottky diodes, and it seems a bit of an overkill. I mean, if you look at the specs of it, 1000 volt peak repetitive reverse voltage, RMS reverse voltage 700 volts, just seems like a bit of a overkill for what we're trying to do. So, of course, we can use the 5N 1N5819. The peak reverse voltage is 40 volts. So forward voltage drop 0.45 volts maximum. So why not use the 1N5819? It's cheap. They don't really cost that much, and we have plenty of them in stock. So if we come back to our circuit, that pretty much takes care of our power supply. We've got our input, terminal input, we've got our switch, we've got our fuse to protect it, we've got our MOS for transient noise suppression, we've got a transformer, we've got a bridge diode, and we've got our LM317 adjustable voltage regulator. Again, these are cheap garden variety components. You should have plenty of these in stock. I just want to make this a little bit neater, so I'm going to delete that. It looks a bit more, I know it's pedantic, but it looks a bit more, you know, neater. Okay. Okay, so we will save that. So that takes care of our power supply. So where we left off last time, we have this battery input. We have a voltage divider to scale down our battery input to something we can work with. We talked briefly about an op-amp, the inverting inputs and non-inverting inputs and what they will do. We're using the op-amp as a comparator. We're not using it as an op-amp. So what we need, I'm going to take out, or let's rather just do this. We'll move that one out the way. We'll bring that one there. And that up there. The first part that we want to do ideally what we should do is our battery, we've got a positive and a negative coming in from the battery. I know in this application that this battery reference, the 0 volt here, is referenced to mains earth there. I know from the installation, I know the guy I'm building this for. He has done that for us. He's tied his negative of the battery terminal to his mains earth coming from his power provider in South Africa, Eskom. Ideally what we would want to do, because maybe they leave it floating for whatever reason, wouldn't be ideal, but for whatever reason they might use this floating, then that means that that reference that we're getting here is not tied eventually to our ground. So what we could do is we could put in something to isolate that. I'm not going to do it with this circuit. There will be another circuit where we will do this with a microprocessor. I'm doing this to teach you the basic jelly bean components. But what we could do is we could put a nice optocoupler or something in here that would basically isolate that circuit from what we're going to do here. We don't have to do it in this application because we are going to well, we know that our 0 volt of the batteries is tied to our mains earth. So the first thing I want to do though is I want to do something that op-amps are quite good at, is I want to buffer the circuits. Why can't I copy it? Copy. Thank you. So we're going to put in our our supply rails. Like that. Probably we need to make it a bit higher. but anyway. So if we took this op amp output like that, and we just tied this inverting input to the output like that, basically what we have is a unity gain buffer. A unity gain buffer is what? Well, as the name implies, unity, a gain of 1. In other words, 0 gain or no gain. What you put in is what you get out. Why are we doing that? Well, what we're doing is providing a high impedance input to our circuit. So we are giving whatever's going in here a very high impedance, and we're giving ourselves a low impedance output. We are just buffering the circuit. So that takes care of that. What we could do is we could put in because the nice thing with LM741 is we have this what they call the offset nulling. It allows us to eliminate, we can put a variable resistor in between here and ground, and we can eliminate whatever offset, whatever difference there is between these two inputs. And that's nice because it allows us to cancel out that offset or to make the op amp more accurate. So let's see. Oh no. Variable. Not quite. Let's see. Yeah. I like this one. Let's use this one. So if we put something like this in, let's move that down. So what we could do is we could have our variable resistor there, like that. And if we move that up, we could have something like that. So all that's going to do is trim out whatever offset is between those two pins, 2 and 3. We would trim it basically and take it out to ground. Nothing fancy. So what we've done here, we've tied the output back to the inverting input. No resistor dividers or anything like that. So 0 or basically unity gain. So whatever is going on the input will be happening on the output. So we've created a high impedance buffer to our battery. If we basically do a bit of maths, how about if we made, you don't even have to do much maths, if we made that 27k and we made that 3k, and let me just get my standard resistor chart out. 3k, 27k standard resistor values. So if we made it 27k and 3k, basically we've got a 9 to 1 voltage divider. So whatever's there we will have 9/10 of that value here, or 1/9 sitting at that point. So 56 divided by 9, that's what you would have here, or 44 divided by 9, that's what you would have sitting at that point. We could obviously go find more accurate values and give ourselves a 10-to-1. I'm not particularly worried about the value at the moment. It's up to you. What we will do when we go to the microprocessor version of this, you will see then I actually divide it by certain things to give us steps, because then we'll go into the micro, the ADC of the micro, but it's not jump to the gun. We are building a basic building block circuit. We are taking this to, or we're doing this to learn the basics of our components. So let's move that up just to make it a bit neater. Right, what we are missing is, over the power rails of this, typically we should be putting in a capacitor. We're not going to use polarized, we're just going to use the typical, let's put it, where can we put it? It can go there. And this capacitor typically, of course I will make this neat later on, is going to be, and we don't even have to think about this, is going to be 100 nano or 0.1 microfarad. Where do we get these values? The maths is done for you a long time ago, but with experience you will find that this is what those values would be. So if you look at the circuit, you will find this in there. But the maths, like I said, the maths has been done, and they've worked out that 100 nano should handle the ripple that would be here, so the bypass is sufficient. So we need to add another note in here. So what I'm going to do, we'll just copy this. And we want to put a note in here. So I'm just going to put it at the bottom, and we're going to say notes. And we want to say or MLCC, so all multi-layer ceramic capacitors, because that will be a multi-layer ceramic capacitor, to be X7R rated. Now X7R has got to do with the temperature stability of the capacitor, because the capacitor can actually act as a resonator, and it can drift badly with temperature. So we want them to be X7R rated. And while we edit, we can also put in a note for all our electrolytics or electrolytics to be 105 degrees C. Rated. Fair enough. So we've got our 2 nodes. So let's save this. So what we've done is we've buffered our battery, created high input impedance to it, and we've created a low output impedance. So now we actually have to do the comparison. We need to set this thing up so that it can drive whatever, and we need to do that. So the easy way to do that now is let us put in another op amp. So let's take this op amp here. Now we are going to take this value, because this is our actual value, right? If we want to call it that. Let's just delete that so we can bring this in a bit more. So that's our actual value. We need a reference value. And the easiest way to do this is to take, let's take another yeah, we could take one like that. Nah. Our pot. Yes, we want something like this. Oh, the wind is quite breezy this morning. So let's just move. Again, we'll have to move our 18 volts up. That's fine. We'll take that to there. We'll take that to there. And depending which way you want to turn your pot, we'll take that to there. And we'll take that to there. So basically, what are we doing here? Our 227K stay the same. No, will they? No. I will need to adjust them. So we'll have to do a bit of maths because we've divided it down. So let's take that value. Oops, I'm still on draw. Let's take that value out. And we'll just put R. So if we set now a value, another voltage divider up here, and we trim this pot, we can make this op amp have a reference value. In other words, we're looking at what's happening over here, and we can set up a trip point over here. And again, we can do the same thing that we did earlier on. Let's just tie this to ground, and we'll tie this to our 18 volt supply. And again, we need our bypass capacitor. So let's move this over. I'm not too worried about making it neat. That we can always do later on. And we can do our offset trimming again. Like that. Now I have worked these out based on the trimmers that I have. I don't want to draw. Come on. This is going to be 5k because that's what I have. And that value is going to be 2.7 meg. And it's got to do with the voltage divider and the current that can go into the LM741, because even though it's, in an ideal world it wouldn't pull any current, it actually does take a few little microamps, if I remember correct. I can't remember the exact amount, but do I have it in my notes? No, I don't. But we can always look at the data sheet. So to summarize this, we've taken our battery input voltage, we've put it through a 9-to-1 divider. We know that the battery is earth or mains earth referenced. I'm just making things neat, I know. I don't need to do that. We can go back and do it and space this so it's the same. We've taken our battery input voltage, that's mains earth referenced. We've put it through a voltage divider. We've put it through a buffer, a 1-on-1 or unity gain buffer, just to isolate it. We're trimming out the offset of the two inputs. We've put a bypass capacitor in of 100 nanofarad or 1.1 mic. We now come to our op-amp that we're going to use as a comparator. So we're going to compare the actual battery voltage against a reference that we determine. So we can set our trip point or our switching point based on this resistor divider here, the 2meg7 and the 5k. And this op-amp is now going to do that. Is going to act as a comparator for us. It's either going to be high, in other words rail voltage, or low ground. The thing though with this op-amp is it cannot go rail to rail, and we'll see that now. So because I have 5k pots, so I'm going to make these 5k. Massive design choice there. I have it, so I'm going to use it as that. What else are we missing in here? Nothing. Right, so now we need to use this op-amp to drive something. We can delete that one. Well, we want to be able to switch off. The idea of this circuit is that we're comparing the battery voltage. We want to see where it is, so we know if our battery charge or battery store is going down, we know, our solar panels are not keeping up or whatever. So the idea is that this guy wants to be able to switch off his geyser if the geyser happened to be running, because a geyser is a resistive load. It's on or it's off. It's pulling 2 kilowatts or 3 kilowatts of power, and that's it. It's not in between. It's on and it's pulling it or it's off. So the idea is to be able to switch out for this application. Obviously when we do the microcontroller one, we will build, you can add 8 different circuits or whatever. But for this one, we want to be able to switch the geyser on or off. So what we could do is we could put in a relay. Oh no. Oh no. Close enough. But I want more than that. I want a double throw. There we go. So single pole, double throw. So we could put in a relay to now switch his geyser on and off. Let's just say that is going to be like that. So the way we've got our op-amp configured, if the inverting input is below the non-inverting input, basically what we are going to do is we are going to switch. I just want to move my notes out of the way. We are going to switch off. No. I must just think of this. If our inverting input is below is below our non-inverting input. In other words, that little negative there. So if this voltage here is below this, the non-inverting input, that means our output is going to be high. So this relay will be energized. Okay, that's fair enough. Why do we want to do that? It means our battery power is fine. So if the voltage is below, it's fine. We'll keep our relay energized. In other words, we can power our geyser. If the voltage of the inverting input goes below our non-inverting input, we de-energize the relay and we drop our geyser out. So that is fine. The problem is that the output of this op-amp, first of all, is a very low impedance, but it can only supply 25 milliamps. So we need some way to drive this relay. So the easiest way to drive that relay is let us use a simple jelly bean transistor, 2N3904. And we'll put it there. So if we come to our data sheets, let us pull up the 2N3904. Our 2N3904, small signal NPN transistor, and we're using an NPN because we want to, if we switch, we put power to the base, we put current to the base, we'll switch the transistor on. So, what do we know about the NPN? It's through hole, which is great for what we're doing. It's a TO92 package. They give us the pinouts, applications. It's suitable for TV and home appliance equipment. Small load switching transistor with high gain and low saturation voltage. And then they give us our absolute maximum ratings. Collector base voltage 60 volts, collector emitter voltage 40 volts. Well, that's fine because we have 18 volts to work with. Base emitter voltage 6 volts. Collector current 200 milliamp. So we can drive up to about 200 milliamp with this thing, maximum. Power dissipation, I don't care about any of that. We don't care about. So our 2N3904 jelly bean transistor, you should have many of these in your box, the equivalent, the BC337 and that sort of range. They can just drive more current in higher voltages. But anyway, we need to set this up. So now, remember we said the LM741, unfortunately, is not a rail-to-rail op-amp, which is fine because I've got plenty of them in my box, so that's why I'm using them. And it's dead cheap, and I can use this trimmer to null the input offsets. So how do I go about this? Well, if this voltage here, if this thing is switched off, so let's draw in the output. If the output of the op-amp is not going to be at 0 volts, it's going to be 1.5 volts above our ground when it's off. And conversely, when it's on, it's going to be 1.5 volts below our 18 volts, so it's going to be 16.5 volts. Well, we can do a little bit of magic here. Let us go look at our humble 1N4007. The thing we know about the 1N4007, if we come to the data sheets, is it has we'll just come down to this graph here. The instantaneous forward voltage, in other words the voltage drop across that diode, starts at 0.7 volts. So it will give us 0.7 volts, and as the current goes up through it, the volt drop will rise, but it starts at 0.7. So if we go and con our circuit, let us do that. Let us we'll put 1 on the emitter. The leg with the little arrow is the emitter, and we know it's an NPN because the arrow is pointing out, so never point in, NPN. Or if the arrow was the other way around, it will be a PNP, so point in, please. That's just how I learned it. So the thing is, we need a few things to switch this transistor on. It's a current and a voltage driven device. So to switch this transistor on, I need to have on that point on the base, this part with the line being the base, in other words pin 2 on this pin out, I need that voltage at that point to be higher than 0.7 volts, right? And I need, because we're going to use this transistor as a switch, we're going to drive it hard. In other words, we drive it into full saturation. We're not driving it as an amplifier where I use a bit of, as I adjust the current into the base, I will adjust the current, I will amplify the current flow through the output. I'm not interested in that. I'm interested in switching this thing hard, so it's hard on, hard off. So I need 0.7 volts there, higher than that. So if I raise the ground by 0.7 and I go and put in, let's just delete that and we'll move it over. And we can just bring this over a little bit. So if I put a diode there, So I've got a 0.7 volt drop there, a 0.7 volt drop there, and a 0.7 volt drop here. Well, basically what I'm doing is I'm elevating, or I'm offsetting the offset required for the op amp. So the op amp, in other words, what am I doing? I am making sure that I can switch that transistor. I'm making sure that whatever voltage drop I end up with there, so if this thing was off, it would be 1.5 volts. I'm getting rid of that part of that 1.5, and I'm getting rid of more of it. I'm bringing that up. So I'm actually bringing that switching voltage here, I'm bringing, so it's 0.7 here plus 0.7 here. Do you follow me? I'm dropping here 0.7. I need 0.7, this base point to be higher than 0.7 to whatever that emitter is. So that 0.7 plus that 0.7 is 1.4 volts. But I still have 1.5 volts at this point, so I'm going to have 0.1 volt here. So chances are that transistor is still going to be on. So drop another 0.7. So we make sure we switch that transistor off, and we make sure we switch it on conversely. So that's just a nice Jippo trick to be able to switch it, to make sure if we're not working with a rail to rail op amp, to be able to switch it off. So we need to do a few things more. Let us put in a resistor, because we need to limit the current going into the base of the transistor. So we'll move it over a bit more. We'll move our relay out the way. Just move this over. Of course, I will come in and make this neater afterwards. Now, we need to calculate this base resistor. The simple formula for this is the input voltage here to switch it on, less the voltage drop required there, divided by the current in the base. So if we come back to our data sheet for the 2N3904, let's bring it up for you, and we come down and we look through the data sheet. So here they talk about the base emitter saturation voltage, basically at, if the current going through the collector is 50 milliamp, we'll have 5 milliamp here. We need 5, so if we want 50 milliamp flowing through our collector. Now we know the load that we have to drive of the relay coil is 30 milliamp in this case, so I can't use this 10 milliamp. I use this 50 milliamp. Well, the minimum value is 0.65, the maximum value is 0.95. So if we do the maths, we say we'll work on a collector current of 50 milliamps. We need a base current of 5 milliamps. So the Vn minus the VBE, or the base drop, and we choose the VBE of 0.8. Basically, this resistor, let's bring our KiCad up, is going to be, let's take that, come on, it's going to be 2K 2. Now I could have used, well, why didn't I use 1N4, 1N5819s here? We know our 1N4007 is going to give us 0.7 volts of a volt drop. Let's go look at our 1N5819. Do they give us the volt drop here? VF max 0.45, but that is going to be dependent on the current flow. But anyway, yeah, so yeah, we talk about how can that be VF max 0.45, and then later on they go on. Okay, so maybe the 1N5817, but we need 1 amp, so let's say it was 0.55. If we come back to our drawing, so if we had 0.55 here, so that's 1.1 if we made that. We could use 1N5819s. Let's see. 0.55 plus 0.7 plus 0.55. Let's do a little bit of maths here. You probably won't see the calculator. 0.55 times 2 plus 0.7. Yeah, we could use 1N5819. So let's change that. 1N5819, not exclamation mark 1. So we can actually use 1N5819s. So we now need to drive this thing, but how about if we wanted to know when it was on? We need an LED. Before we go on, we need a few things here. We switched this thing on. We want to take out any little ripple noise that's happening here. And when we switch it off, we want to be able to discharge that capacitor as well. So let us put in copy that resistor. Let's put a resistor in here. And let's put a capacitor in here. Zero 0.1 seems fine. We'll make that 10K. We'll just move that over again so that they look evenly spaced. So what are we doing here? Nothing fancy. All we're doing is for whatever noise is happening here, we want to keep that output filtered, nice and constant. So it's either be I, off. So any noise, ripple, anything like that, this capacitor will just bypass it from the transistor. In other words, bring it to ground. It will AC couple whatever noise to ground. When the transistor now switches off, we don't want to keep it on. We'll be able to discharge this capacitor through that 10K resistor. 10K, because we don't want whatever we're driving to go straight to ground. We want it to ideally go into the base of the transistor and very little leakage current to ground. So we need one more thing. or we don't need one more thing. Ideally we would like to know if it's on. Is the thing switched on? So if we put an LED in there, we're obviously going to need a resistor for the LED. Again, we can go calculate and do the maths, because we know the volt drop across the transistor across the 1N5819. We know the current flow and voltage we need through the resistor, and it's simple ohms law. I'm not going to bore you to death. So if we do the maths, roughly that's going to be 120 ohm. And again, that will come from our 18 volt rail. Let's just do it like this for now. We'll come back. I will come back and draw it neater later on. So that will tell us if this transistor is switching. So is switched on. In other words, is our output high or low? Is our geyser allowed to be on or not? So again, we do the same thing here. Basically, we will have our relay. We need a current limiting resistor on the relay, and that is 300 ohms that I've calculated. One thing that we do need on this relay is we need a flyback diode over the coil, and we need that because we don't want to damage the transistor, because as current flows through this coil, a magnetic field is going to build up into it, because the coil doesn't like a change in current direction. So the current is flowing through the coil. Now when we switch this off, this transistor off, this current's got nowhere to go. So the voltage at this point is going to rise very, very sharply. So to give that current and voltage somewhere to go, we will put this flyback diode in the circuit. So we just move it up like that. And bang, like that. Okay. Let's just make it neat. Well, semi-neat. Of course, I will go back and sort the spacing out. And if we put our terminals like that, basically that completes our circuit. What have we done? Well, we've taken our battery input, we've buffered it. Out of the buffer we compare it against our own reference. And as long as that battery voltage is lower than our reference, we are going to be, so I've got this on the wrong point then. So as long as the battery voltage is below our reference, in other words our battery is not high enough, we are going to switch on this transistor and relay. Because we switch the transistor on, it allows the current to flow for the relay, and basically we're going to switch our geyser off. So we're not allowing our geyser to be on if the battery voltage is below our reference. We could of course do it the other way around by swapping these points around, the non-inverting and inverting input, but if I remember correctly, I did this for a reason. Yes, because ideally your battery is always going to be charged and whatever, and I don't want to be holding a relay in all the time to keep your geyser on. I want to hold the relay in to keep your geyser out. And if everything fails, then the relay will default to its normally closed state, and the geyser will be allowed to power. So that basically takes care of our circuit. Of course we can go and build on and on and on this, or based on this, and use more comparators at different stages, which is really what we're going to put in again, except there I will use comparators that I have. But we could put in strings of LEDs and use comparators at different voltage levels to switch on an LED bar. So that way we would know what our battery level is. There is really not much to that circuit. So what we could do is take, let's copy, and we'll just put in, let's say 1, 2, 3, 4, 5, and so we go on. 6, 7, why am I being an idiot? Copy the block. Now, simply put, if we did that and we had and we gave it a fixed reference voltage, something like that, and we took that to earth, and that had a fixed reference voltage up there, and if we took these points out here like that, so we keep going. Why am I doing that drop? Let's delete these points, delete. And if we did this, and we went and put in what do we want? Let's put it like this. Of course my spacing is going to be lousy, but whatever. If we went and did this over and over and over on each point, and we used pin 3, let's do like this. Something like that. And all we did is we gave this a fixed voltage reference, V ref, and this we made our bat V, we copied that and we took our battery voltage from where would we take it from? Basically after our buffer, so we took that point there. We could use these to drive an LED string, and that would give us an indication of where our battery level is in however many steps we decided that we wanted to go in. So 1, 2, 3. So you could have 10 steps, and you would know basically in percentages of, or 10% per block, so you would know where your battery voltage was lying roughly in a nice bar indication. So anyway, that completes our basically our power monitoring circuit. We've used an op-amp as a buffer, we've used an op-amp as a comparator to switch the transistor, basically to switch in a relay that will either switch our geyser on and off based on what our battery voltage is doing. And we've said we can take that same battery voltage and add in a whole bunch of comparators with a voltage divider, and by doing that we could drive LEDs and we could have an indication as to the state of where our battery voltage is at that time. So I'm going to switch, or I'm going to leave the video at that point. What I will do is go and neaten up this schematic, and I'll add in this indication circuit, and then what we'll do is we'll come back in the next video and we'll actually build the circuit and we'll test it and see how it works. We'll put a scope on it and a power supply and whatever, and mains, and we will actually see how well this circuit operates, how well it works. So anyway, until the next one, take care, stay safe, and cheers.